NCBM 0324, Section 1.4, Evaluating Functions Using Function Notation, Part 1. Function notation is very important when it comes to math. In any math class, you're going to end up using function notation. So a good understanding of what it means will help us in the future. When we say function notation, we really mean writing something of the form y equals f of x, mainly that f of x part, is what we call the function notation. And what this really means is that my variable y is a function of x. So I have some sort of equation, y equals, and I have some powers of x, some operations on x. And if it has that definition of a function, that just simply means that I can replace that y with this other notation. So that idea of f of x is the exact same thing as y. Now you may be wondering, why do we even use it if y is so much nicer to write down? Well, the nice thing about function notation, it not only tells us the y value, this is all the y value here, but it also describes and it shows for us in the notation what x we use to make that y. So that's what this inside part of our function notation represents. This is the value that's going to go into the operations on the other side of the equal sign. So when we write y equals f of x, we assume that the variable x, the one that's inside this inner part here, is going to be an independent variable. And the y, which is the same thing as the f of x, right, the whole thing all together, these are going to be referred to as the dependent variable. Dependent variable. Now the idea of the independent dependent will help us remember what exactly this function notation is representing and telling us what to do as well. So when we are given some sort of x value or we get to choose the x value, that's our starting point. Then to find the y value, the f of x value, we're going to take this and we're going to plug it into whatever operation the equation calls for. So that's why we say that this y value depends on the x value. Right? Traditionally, we use f to represent our functions, but we could use any other letter. We could use F, G, H, those are the common ones we see a lot of times, but they all mean the same thing. It's all that idea of the f of x is a function of that x value. And we read it in that way. We read it f of x. Sometimes you may want to read it f at x, and that's another way of reminding us that how we got the y value, well, we use this particular x value inside. One last thing before we see an example. The parentheses. It's very easy to fall into the pattern that parentheses means multiplication. In this case here, when I write f of x or f at x, this does not mean the function f times x. This means this f is the name of my function, and I'm going to be evaluating it at this x here. So this x is part of the notation. It's not another multiplication of a variable. That's the same one whole value, the same thing as that y. So be careful with that. Let's see how this works. Example 1. Evaluate the following functions by using the skeleton method. So the skeleton method is going to help us as we're starting off using this function notation for the first time. Once you get the hang of it, you may not need it, but it's a good place for us to remember what this function notation is representing and how to actually apply it. So looking at our table, we have some functions on the left over here. We have a couple of skeletons set up, and you can kind of see why it's named a skeleton method. And then we're going to do some plugging in and some work to find the values. So in our first function, we have f of x is equal to 2x minus 3. So notice the right side has my variable x. So when I evaluate something here, whatever x we have inside of these function parentheses here, I know that's what I'm going to use to plug in on the other side of the equal sign. So then by a skeleton, without an actual value in there, whatever we have in this empty spot, whatever may be inside that parentheses, that's what goes into the spot where the x used to be. So it's like a substitution, a replacement of the variable x with a certain number. In our third column, they're asking us to find f of negative 2. So we see that negative 2 is inside of our parentheses. That's in this spot that's going to get plugged in. And it's going to go as well into the space where our x used to be. So I'm going to substitute plug in a negative 2. Another good thing about those parentheses, they help us keep track of signs, right? This one's a negative, so we got to always take a little more time and care with the negative. So then we have a nice expression on the right-hand side. We have practiced this already, so we can use our order of operations. 2 times negative 2 gives us a negative 4. Minus 3, keep the minus 3 on the right there, keep it going. And then we can subtract these, negative 4 minus 3. We could say then that f of negative 2 is equal to negative 7. And that would be our answer. That's our function value. So let's think about why this is different and why we do this and why it's important. Well, we said previously that the y is the same thing as f of x. So if I write this back in terms of x, f of x is equal to 2x minus 3, but I want to only think about it in terms of y, and I simply write, well, y equals negative 7. This doesn't really tell me too much about how I got the negative 7. I know that something plugged in here gave me that number, but just the y by itself doesn't tell me that. And that's why this notation is really handy. Not only do I know the y value is negative 7, but I know what x value I used to make that negative 7 happen. In fact, if I wanted to, right, I could even write this out in a few other ways. I could say, well, the x value is negative 2, the y value is negative 7, right, separately like that. Then we could see the relationship there. If I'm thinking about a graph, an ordered pair, x is negative 2, y is negative 7. In math, there's always a lot of ways to write certain ideas down, and that may be confusing because they all mean the same thing, but every notation has its place. So sometimes function notation is more useful, sometimes an ordered pair is, sometimes even just that y, right? Sometimes we just need the y value. So it's good to know our options and that there are options out there. Let's try the next one. We have g of x is equal to 5 minus 3x. So there's our function. We have our function name. It's a g this time, and that's fine. It's still all of this g of x part here. The stuff on the left side of my equal sign, that's still representing the y value. Let's go ahead and fill in our skeleton method. What is that skeleton going to look like? Well, we were saying anywhere there's an x, right? We're going to put a space to fill in our values, whatever it may be. So I'm going to have g, whatever they want us to plug in. So I'm going to leave it blank there. There's my skeleton starting. 5 minus 3, here's my variable. So that's where I'm going to leave a space to plug in a number or another value. So then the last part of the table, we have g of 2 is equal to, got to figure that out. So I'm going to copy down my skeleton, right? G of x is 5 minus 3 times this blank spot. And in this case, we want a nice positive 2 into that blank spot. We're substituting, plugging in a 2. And then we go with our order of operations. So then g of 2 is going to equal to 5 minus 6. So g of 2 is equal to negative 1. And we have our answer. In other words, the value x equals 2 gives me a function value of negative 1. The x is 2, the y is negative 1.